A really common use of calculus techniques like differentiation is in optimization problems when we want to find a maximum or a minimum, as I've written here. Now, I've got a few tips here for you to follow. Uh, I think it's worth looking at them. So when you can, if it makes sense in context, draw a diagram. The second thing is it's kind of almost a literacy point, this one. Use the information to model the problem as an equation. Now that requires you to read the problem, then reread it again, underline stuff, circle stuff, highlight stuff, whatever you need to do to keep pulling the information. And as you build your model, keep referring back to the question saying, have I captured all the data? Have I used the data properly? That kind of thing. I cannot emphasize that enough. Reading the question once, then going through it probably won't cut the mustard if it's a complex problem. Once you've got an equation, though, you've modeled it somehow in algebra, then you can get to solving it. And then this last one is also kind of a literacy question as well, and that is answer the question. What was it actually asking you for? And I'm going to illustrate this by looking at an example here that I've pulled from the 2018 exam. It's question 46. Now, question 46 is a calculator-based question, so that makes it a little bit more friendly in terms of using your graphics display calculator. For this video, I'm going to be using my scientific calculator, and I won't be using the GDC. So I'm going to be using a much more what we call an analytical approach, where we use the algebra to solve the problem rather than leaning too heavily on the GDC, just to model it really. I might do a separate video if I've got time where I lean more heavily into a GDC so you can see how it works. But yeah, we'll see how we go with that one. So let's unpack this problem. A rectangular piece of card has dimensions 8 centimeters by 5 centimeters. You will have 4 equal squares cut out of the corners. Okay, cool. I think we got that. It's then folded to form an open rectangular box. I know what that looks like. I can visualize that in my head. So as I'm reading this out, I'm not really paying attention to the numbers as such, but just trying to think about what it's really getting at here. It's then folded. Okay, so I can imagine a box. And then here's the bit which is really critical. Find the dimensions of the box that will give maximum volume. Okay, so that's the question. That's the question, I suppose, that I have to answer. What are the dimensions? Okay, so going through it again now, you could use a highlighter, you could use an underline. I might use a highlighter, and let's see how we go. Don't have a yellow highlight on this, it's quite annoying. I guess I'll just use a purple one. So a rectangular, okay, so I guess that's important that I know that it's rectangular. Dimensions are 8 by 5 centimeters, cool. 4 equal squares are cut out, okay, and then it's a rectangular box. Okay, okay, I've got that. I think I'm all right. It's not too tricky to figure out, I think. But as you can see up here where I've said draw a diagram, that's exactly what we should do to start off with, because it helps us make something concrete, I suppose. So it's a rectangular piece of card that's dimensions 8 by 5. Now, I'm not going to spend too much on this. I'm not going to be getting my ruler out or anything like this. I just need to know roughly what I'm dealing with. So it's 8 centimeters. I probably haven't done this very well in terms of proportions there. And then what is it? 4 equal squares. Having highlighted it, it's sort of in the question, I can just confirm what's going on. So the squares are going to be in the corners here somehow. They're the same, cut out of the corners. So that's okay. That makes sense. Okay, and I can see now that if I take off that dotted bits there, I'm going to have a net for a box, aren't I? An open box. So that kind of makes sense already. I can already see that I'm going to have a little chunks cut out, and I haven't been told what those little chunks are. So whenever you've got an unknown, it's good to put a label on it, and this being algebra, X is what I'm going to use for that. I'll just zoom up for a second to do this. So it says 4 equal squares. So the same size square, so all of them are X, and it says square, so it's going to be an X by X. Okay, so that's all right. I think that's all I need to do here. Okay, and it's going to be cut into a box, so let's see what that looks like. Just a really rough diagram. Okay. oops, that went a bit too far, didn't it? Not that it really matters, but there you go. Okay, so there's my box. Now let's have a look at the dimensions. Now, if I'm folding up the box, this is going to make this x here. All of these lengths here are x. The height of the box is x, I suppose. What does that mean for the other two dimensions? Well, if this is 5 centimeters, I've got meters there, but I meant centimeters. If this is 5 centimeters in total, and I've got an x missing here and an x missing there, that'll make that a shorter one, isn't it? So I'll just put it here. It's going to be 5 minus 2x. And the longer one is going to be 8 minus 2x, same sort of logic. Okay, so now I've got my 3 dimensions written in. So I haven't tried to solve the problem. I've just tried to set it up as a model, because what I'm heading towards is an algebraic equation. So what I can see I can vary is I'm constrained by the fact that it's an 8 by 5 centimeter piece of cardboard, and my variable is that I can change the size of this square. That's x. So I need to set up my equation based upon that. Now, I'm looking for the maximum volume, so my equation is going to have to be volume. So let's put down a volume, and because I've got a variable of x, I'm going to call it v of x. You could get away with just calling it v, but I think v of x makes it look more functiony. So we know that volume is just length by width by height, right? So let's just do that. I'll put height first because it's simplest, x. And then what are my two other dimensions? 8 minus 2x and 5 minus 2x. There we go. I've now modeled it as an equation. So now I'm on to sort of like step 3 now. Can I use that model in order to solve the problem? Before I go any further, I think I might just take a moment to expand that, because I know I'm sort of thinking ahead a little bit, and I can see that I'm going to have to use calculus, differential calculus, in order to find the derivative, because when I find the derivative, I can then find a local maximum and local minimum, that kind of thing. So I can sort of see where I'm headed towards here. If I'm going to find the derivative, I'm going to have to use the power rule. If I'm going to use the power rule, it needs to be a sum of pluses and minuses between powers, effectively, not the products like I've got here. X times 8 minus 2x times 5 minus 2x. It's a product, so I don't have a rule yet. So let's just expand it, because I know that's where I'm going to have to go. So that's going to be x outside of, let me see, 8 5s are 40 minus 8 2s are 16, x minus 10x plus 4x squared. And that will give me, now in my next line, I'm going to write this in descending powers of x, because it makes me feel happy. It's kind of like a standard way of writing things when you can, and if it makes sense. So don't be shocked by what I'm doing here. So I'm multiplying this by this to get 4x cubed, because that's the highest power. The next power is x. So in my head, I'm just collecting like terms here. Minus 16 minus 10 is minus 26. And then I'm multiplying it by x to get minus 26x squared. And then I've got 40 at the end there. So I've got plus 40x. There we go. All right, now let's try and find, so that's the volume. So substituting values in for x will give me varying volumes. And, it doesn't hurt to start thinking about what are possible values of x as well. Like, for example, I'll leave it as a bit of a thought experiment for you, but I know that the maximum length that x can be is 2.5. I wonder why. If you have a think about it. Back to the main problem, though. I need to find a maximum volume, and I know that the maximum volume is when v dash of x is equal to 0, right? That's what we've been doing. We know that there are turning points in our graph when the gradient function is equal to 0, flattens out. Okay, it might be a maximum or it might be a minimum. We don't know that, but that's where we're headed. Okay, so let's do v dash of x to start off with. V dash of x is equal to 12x squared minus 52x plus 40. I hope this is routine work I'm doing now. If it's not, make sure you practice more your power rule. And we set that equal to 0 because that's when it's a maximum. Or a minimum. That's what we're going to try and figure out. Okay, so I now need to work out what x is. This is just a quadratic. So I'm going to use my usual quadratic techniques to find out what x is. First thing I'm noticing is that 12, 52 and 40 have a common factor of 4. So I'm going to divide both sides by 4. Okay, and that gets me to 3x squared minus 13x plus 10, is equal to 0. So that's pretty cool. Now I'm going, this is where your GDC can then work out what x is without any more dramas. But because I'm trying to do this more analytically, I'm just going to do it by factorization. So I'm going to multiply 3 and 10 together, and that gives me positive 30, and I need to aim for minus 13. So if I group these together, two numbers that will multiply together to give me 30 that multiply together to give me 30 that will add up to 13. That's what the plus there means. Means they need to add up to 13. So that leaves me with 10 and 3, because 10 3 is 13, 10 plus 3. I've got a minus out here. There's a minus here. So that means the biggest number becomes a minus. And then what else do I need to do? Make the other one a minus as well to make it to minus 13. Put 3x on top here and cancel down. So this is the diamond method. We did this in our first unit. Look back if you can't remember it. It's a really nice way. It's a bit magical, but it's a really nice way of factorizing an equation. So 3x minus 10x minus 1 is equal to 0. And therefore, we've now got x equals 10 over 3 from the first factor. Or we've got x equals 1. Now, what we don't know is which one's a maximum and which one's a minimum, okay? But this is as far as we've got so far. Now, I need to switch to the next screen, so we're going to miss all this. I've got a printout next to me so I can sort of see the work already, so you might need to rewind the video a little bit, perhaps, if you just need to make sense of what I'm doing next. So we need to check to see which one of those values is a maximum, which one's a minimum. Now, with a GDC, you can probably just graph it, and you could see which one's a maximum and a minimum. But to be honest, if you had your GDC and you just graphed it, then you could see where the maximum minimum is anyway, right? So it's a bit artificial. In fact, the question actually specifically says, I've sort of modified the question for this video. The exam question says, use calculus techniques to determine the maximum, which means that you're forced to do it, even though with your GDC, you could just graph it without any more thinking. So there you go. I've told you before that mathematics can sometimes be a journey into the artificial, while we try to get you to practice skills that you need, but we can never get a scenario where you don't have access to a technology which might make it easier and stuff. So I get that a little bit. Okay, so what we do to check it is use that sign table that I've explained to you before. So let me set it up first. So we've got, I'm just going to do it freehand writing here. We're going to have, this is the check. I should have written that at the top. We're going to have x values. We're going to have a look at the derivative, and we're going to have a look at what that would mean to the function itself. I guess I should use v dash and v, really, to be honest. So how about I change that so it's all consistent? So v dash and v. Okay, so our two values are 1 and 0. 1 and 10/3. So I'm going to leave a gap between, as I've shown you before, another gap, and then 10 over 3, which is what, 3 1/3, and then another gap here. So that's the gaps that we've got. So we know v dash is 0 here, and v dash is 0 here, which means we've got a flattening out of the curve there. It's going to be a maximum or a minimum. And now I'm just going to choose my values either side of 1 and 10/3. So this, I think I'll use 0. That makes the most sense to me. Although x can't technically be 0, it does make sense in terms of the function. I'm only using 0 to get an idea of whether it's going up or going down. So that's okay, even though technically x couldn't be 0. It's okay in this context. And then between 1, so remembering that 10/3 is about 3 1/3, between 1 and 10/3, I'm going to look at using 2, like so. And then after 10/3, 3 1/3, so just use 4, I think, or maybe I could use 10 if that might make it easier. I'm not too sure. So there's my values I've chosen, but I've literally chosen them because they fit either side. I'm really hoping that 1 is going to be the maximum, because x can't actually be 10 thirds. And again, why can't it be 3 1/3? Maybe go back to the diagram and see whether you can figure out why. But I do need to do the check though, because it might be that if 1 is a minimum, we could be in a bit of trouble here. Okay, calculator. So now I'm looking at my function and I'm just plugging in the values if I need to, until I can get a sense of whether it's going to be positive or negative. So my derivative function was, just to remind you very quickly, 12x squared minus 52x plus 40. So if I substitute in 0 for x, those first two terms will disappear. I'm left with a positive 40, right? So that means that I'm definitely going to have a positive value here. So we have a gradient that's going upwards, which is good news for us. It looks like it might be a maximum at 1. But I'll go through to check. Maybe it's an inflection. It shouldn't be. I can't imagine it would be, but maybe it's an inflection. So now I'm going to look at the value of 2. So I go back to my formula here, which is 12x squared. So I'm going to go 12 times 2 squared and minus 52 times 2 plus 40. Hope the value is negative. There it is there. Whoops. Well, can you see that? Okay. Oh, man, sorry. So negative 16 from that calculation. So that's good to know. So that's negative. Again, as soon as you get a sense that it is going to be negative, you can sort of just put negative in. So there we go. And then just to cap it off, it's probably not necessary, even in an exam situation, to be perfectly honest, but I'll do it anyway. 12 times 4 squared. It's nice to sort of confirm everything is working right. One reason why it's really good to do this, actually, even though it's not strictly necessary, is because it gives you a sense of, like, if you get an anomalous value, then you can think, oh, shivers, is my use of calculator wrong? Is it that I've actually modeled it incorrectly? That kind of thing. So it's useful to do, because everything that confirms everything that you've done gives greater certainty to your answers, right? If you've got time. Obviously, if it's the last 10 minutes of the test and you've only got, 8 minutes to answer this question, and it's an 8-marker question, then, you just got to get it out, right? But if you've got time to do it, it can only help confirm marks. And every time you can confirm marks and shore up that you've got the right answer, I think the better it is for you. Really, you're really locking in those marks as long as you've got time. So you can see here the calculation has given me 24. It's positive. So I can write a positive in here, and that gives me an upslope again. So you can see I've got this kind of thing, with this being a maximum at x equals 1. Okay, so max at x equals 1. And this is where you need to be mindful, right? You can breathe a deep sigh of relief. You can go, oh, thank goodness, I've worked out the maximum is at x equals 1. But that's not all, because the question said find the dimensions of the box that will give maximum volume. So I haven't done that yet. I haven't given the dimensions. So I need to write down, therefore, the dimensions are 5 minus 2 times 1. Oops, wrong way around there. 5 times 2 times 1, which is 3. Centimeters. If you don't put the units in, you will lose marks overall in the paper. 8 minus 2 times 1, which is 6 centimeters. And finally, 1 centimeter, because that's the value of x. Okay, there are our dimensions: 3 centimeters, 6 centimeters, 1 centimeter. Now, the question did not ask this, but it very well could have. It could have said, find the maximum volume. It didn't, so we're done. We can move on to the next question. But just as an extra added bonus, again, in a exam paper, if it hasn't asked you for it, why do it? But because we've got the time to do it, is 3 times 6 times 1, which equals 18 cubic centimeters. Okay, it's not uncommon to be asked both things. Find the maximum volume and hence find the dimensions that give a maximum volume and hence find the volume, something like that. So do be mindful that you might be asked for both. That's why it's really important. Go back. What was the question? Find the dimensions of the box. Okay, have I done that? Yes, I have. And then you can move on to the next question. So make sure that you're really solid on that. I think that'll do for this rather long video, but this video will suit you for 2 lessons worth, really. We're going to do 2 lessons on optimization. And look, this is just one example. There are so many different examples that you could come across in reality. The technique is the same. They can be more complex or less complex situations, which can result in more complex or less complex modeling. In terms of the exam, technically, you should be given the function as part of the exam. It might say, show that, and then give you the function, or it might be, here is the function, now use it. Either way, it is worth practicing actually working out the equation yourself, because as you can see from this particular problem in this particular paper, sometimes the task is a bit inconsistent with what they say you should be able to do and what happens in the exam. Plus, as a general principle, knowing how to model a situation into an equation is a pretty critical skill anyway, even if you're not going to be examined on it. So either way, practice it. Make sure you remember your dimensions at the end, all that kind of stuff. So enjoy the next couple of lessons where you spend practicing different scenarios and optimizing them. Good luck.